Okay, hello guys. Let's continue our discussion with spectral theory in Hilbert space. Starting with some preliminaries, we are going to quickly review the definition of a Hilbert space with some examples. Okay, look at here. When we say we have a complex inner product space, it means we have a complex vector space like H together with an inner product. Okay, when we say together with a map, that maps gives the inner product like this. This maps from H cross H into complex number. You can see it maps every pair to a complex number such that we have these properties. Okay, like here you can see like the inner product of x plus y and z equals the inner product of x and z plus the inner product and y and z. And together, look at here, this property together with this property means that the inner product with respect to first component is linear. And look at this, the inner product of x and y equals the conjugate of the inner product of y and x, because this inner product is complex value. And the inner product of x, every element with itself, is a non-negative real number. You can see when we say greater than equals 0, it means is a non-negative real number. And the inner product of x and x is 0 if and only if x is 0. Okay, and then this inner product induces a norm on H, something like that. It means the norm of H is defined to be the square root of the inner product of x and x, and that makes sense, right? Because the inner product of x and x is a non-negative real number, so when we take a square root, that makes sense. So this inner product induces a norm on H, so this H together with this becomes a norm space. Okay, but this norm space may not be complete, but if this norm space is complete, then it is called a Hilbert space. So actually every Hilbert space in a Banach space, okay, remember, every Hilbert space actually is a norm space, right? But the norm is coming from inner product. So every Hilbert space is a complete norm space, but the norm is coming from inner product. Okay, but remember, so every Hilbert space is a Banach space, but not every Banach space is a Hilbert space. So remember. And then, okay, let's start with some example here. The set of complex numbers C, okay, I can say the simplest example that we can give is C is a Hilbert space. Actually is a Hilbert space with this inner product. It means the inner product of every two elements of C is defined to be Z times the conjugate of W. It means Z W bar. Okay, so actually C with this inner product is a one-dimensional complex Hilbert space, and of course the norm is given like this. The norm of every element is the square root of the inner product of Z and Z, and the inner product of Z and Z means Z Z bar, and this means the absolute value of Z or modulus Z squared, and then when you take the square root equals the modulus Z or absolute value of Z. And in general, look at here, in general, Cn, when we say Cn, it means the direct sum of C n times. There's a finite direct sum. You remember C itself is a one-dimensional complex Hilbert space, but if we have the direct sum of C n times, which is denoted by this, or Cn, this is a finite direct sum, and this is also a Hilbert space, okay, n-dimensional complex Hilbert space with this inner product. Look at here, The inner product of two elements is given at this sigma zi wi bar I from 1 to n. And of course the norm is defined to be like this, the norm of every element. And what you see here inside is the inner product of the inner product of every element like this with itself, right? Look at here, if you put the inner product of this element with itself, so we have z1 bar, which means the absolute value of z1 square. Here becomes z2 bar, which means the absolute value of z2 square, and so on. So Cn is a n-dimensional complex Hilbert space with this inner product and with this norm. Okay, let's take a look at the next example. Next example. Before we talk about the next example, look at this remark. Actually, this remark is a theorem. We just recall it without proof. That every finite dimensional complex Hilbert space with dimension n, or equivalently we can say every n-dimensional complex Hilbert space is isomorphic or simply equals Cn. Okay, so it means if we have a n-dimensional complex Hilbert space, it is nothing but Cn. Okay. Okay, next we have a very important example here, L2n, which is the infinite direct sum of C complex number. Look at here, L2n denotes the set of all infinite sequences of complex number like this, x1, x2, and so on, such that this series is convergent. Look at here, sigma modulus or absolute value of xn squared is conversion. When I say less than infinity, this means conversion. It means actually L2n is the set of all s squared summable sequences of complex number. Okay, this L2n actually is a Hilbert space, which is actually infinite dimensional Hilbert space, and separable. When we say separable, it means it has a countable basis. Anyway, with this inner product, so L2n is a Hilbert space with this inner product. Okay, it means the inner product of two sequences. Here x and y, each one is a sequence. It's given like this. You can see sigma xi yi bar. Okay, we can show that this series is convergent actually using this. So L2n is a Hilbert space with this inner product. Okay, infinite dimensional, and of course the norm of each element like this, the norm of x is a sequence, is given like this. The square root of the inner product of x with itself. So inner product of x with itself, look at here. Here will be x1 bar, x2 bar, and this means the absolute value of x1 squared plus the absolute value of x2 x squared. So what you see here is the inner product of x with itself. So this will be the norm on L2. And remember, sometimes this L2n could be simply denoted by L2 or even by this notation, like infinite direct sum. Okay. Okay, next look at here, we have a definition. So let's say x and y are two elements of a Hilbert space H. When the inner product of x and y is 0, then we say x is orthogonal to y. Okay, and we denote it by this. you can read it x perp y, means perpendicular. And it's easy for you, it should be easy for you to figure out that if x is orthogonal to y, then y is also orthogonal to x. Okay, you can deduct from here. If the inner product of x and y is 0, then this equals the conjugate of the inner product of y and x. So that must be 0 also. So it's easy for you to figure out. And to tell you, if E is a subset of Hilbert space H, okay, then E perp, okay, you can read it E perp. E perp, okay, P E R P, E perp is defined to be the set of all elements of y. The set of all elements of H like y, such that they are perpendicular or orthogonal to every element of E. Okay, this is a definition. So you can see here. And next, of course, we have this on every Hilbert space. We have this very well-known inequality, Cauchy-Schwarz inequality, which is saying that the absolute value of the inner product of x and y is less than equals the norm x times the norm y for every x and y in Hilbert space H. Okay, so this was like a quick review on the definition of on the Hilbert space actually, and of course it was just a quick review, and there are a lot of things that you might need to know, so you can refer to textbooks on function analysis. Okay, next look at here. Okay, now let's talk about the bounded linear operators on Hilbert spaces. Okay, if you remember, we already talked about the bounded linear operators on Banach spaces. So of course, when we say that we have a Hilbert space, non-zero Hilbert space, okay, it means non-trivial Hilbert space. So every Hilbert space is a Banach space. So if you remember, B of H, it denotes the set of all bounded linear operators on H, the set of all bounded linear operators like T on H. And if you remember, this P of H with operator norm, okay, with operator norm is a Banach space, okay, or more precisely is a unital Banach algebra. Okay, when we say unital, okay, when we say unital Banach algebra, if you remember, we said that the product or the multiplication is given by composition, which has a unit element or identity element, and identity element is the identity operator, and such that the product, which is given by composition, satisfies this inequality. It means the norm of ST is less than or equals the norm S, norm T, which is called submultiplicativity. Okay, so we have talked about this stuff, bounded linear operator on Banach spaces. Okay, here in particular, Hilbert spaces. The operator norm, and this product is given by composition. Now look at here. Next, we want to talk about the spectrum of bounded linear operator on Hilbert spaces. So, of course, if you remember, we talk about the spectrum of bounded linear operator on Banach spaces. So, in particular, Hilbert spaces. So, all the discussion and the definition that we gave about the spectrum and resolvent are valid. Because when we are talking about the spectrum of a bounded linear operator on a Hilbert space, every Hilbert space is a Banach space. Okay, so all definitions are valid here. So now, when we want to talk about the spectrum of a bounded linear operator on a Hilbert space H, if you remember, I said that we need to consider two cases separately. The first case is when H is finite dimensional, and the other case is when H is infinite dimensional. Okay, if you remember, we said that, okay, if we have a finite dimensional Hilbert space with dimension n, or simply if we have an n-dimensional complex Hilbert space H, that H is nothing but Cn. So when we say B of H, it means B of Cn, and B of Cn, which means the bundle linear operator on Cn, this, the set of, or the Banach space of B of Cn, which means the bundle linear operators on Cn, it is actually isomorphic, or simply it equals MNC. It means the matrix algebra. It means the how to say, the algebra of all n by n matrices with complex entries, right? And why do we have this? If you remember, we said that every bundle linear operator on Cn, if you remember, I explained this with one example. Every bundle linear operator on Cn corresponds to a matrix, okay? And every matrix gives a bundle linear operator. If you remember, we talked about this. Every bundle linear operator on Cn corresponds to a matrix. This matrix is called the matrix of T. And every square matrix, n by n matrix with complex entries, gives a bundle linear operator. We talk about this with some example, if you remember. And in this case, I mean finite dimensional case, we said that when we are talking about the spectrum of T, it means we are talking about the spectrum of the matrix of T, or simply when we are talking about the spectrum of T, the spectrum of T is nothing but set of eigenvalues of the matrix of T, which is A. It means when you have a bundle linear operator like T on a finite dimensional, let's say n-dimensional complex Hilbert space, which means Cn, then the spectrum of T is precisely equal to the set of eigenvalues of the matrix of T, which is A. Okay, I mean, this is the case for finite dimensional. Okay, you can see I mentioned. But, and if you remember, we gave an example of a spectrum of a bundle linear operator on C2, two-dimensional, I mean, complex Hilbert space. And if you remember, there we mentioned that, okay, that's the story. Okay, this is the story about finite dimensional. But when we are talking about bundle linear operators on infinite dimensional space, the story is much different. Could be much different. It means you can see here I mentioned. It means when we are talking about the spectrum of the bundle linear operators on infinite dimensional space, the story is different. It means the spectrum could be much bigger than the set of eigenvalues, or a spectrum may not have any eigenvalues. Okay, so be very careful. The story is different, finite dimensional and infinite dimensional. So next, we are going to talk about a very, very important and interesting example about the how to say, the spectrum of a bundled linear operator on infinite dimensional Hilbert space. Okay, we have this Hilbert space L2n, and define this map like T on L2n like this. T maps every sequence. Look at here x1, x2, x3, 2. Look at here 0, x1, x2, x3. We can show that T is a bundled linear operator on L2, which is called unilateral shift. Okay. So T is a bundled linear operator on L2. I leave it to you to check that, such that the norm of T equals 1. Okay. This should be easy for you to figure out. So I leave you as an exercise. Okay, now what do we want to do? We want to discuss about the spectrum of T. Okay, you can see we are talking about the spectrum of this bounded linear operator on L2, which is an infinite dimensional Hilbert space. Okay, first we want to show that T has no eigenvalue. Do you remember in finite dimensional space, a spectrum precisely equals the set of eigenvalues, but here we are talking about infinite dimensional space. So we want to prove that T has no eigenvalue, then we compute or describe the spectrum of T. Okay, I have done here for you. Let me step by step explain for you. Okay, look at here. First, we want to show that T has no eigenvalue, right? Okay, so it means we have to prove that no scalar lambda in C is an eigenvalue of T. Okay, suppose the otherwise. Okay, suppose the otherwise, it means there is a scalar like lambda such that it is an eigenvalue of T, and this means there is a non-zero vector or non-zero element in L2 non-zero, such that we have T of x, okay, let's say simply we call this one x. Tx equals lambda x, okay? Then you are going to see that we are going to get contradiction. So to get the contradiction, we consider two cases separately, lambda 0 and lambda non-zero. So look at here, if lambda is 0, the first case, the right hand side will be completely 0, right? Okay, you can see in the next page. So if lambda is 0, look at here, the left hand side is tx, right hand side is lambda x. So this is tx actually, which is 0, x1, x2, and right hand side becomes 0. So we have this, and this means, look at here, 0 equals 0, x1 must be 0, x2 must be 0. So by comparing the left hand side and right hand side, we realize that each xi is 0, okay? And this is a contradiction. Why? Because we said that, look at here, we said that there is a non-zero element. It means there is at least one component non-zero, okay? So this is a contradiction. Now, we suppose that lambda is non-zero. Again, we get contradiction. Okay, if lambda is non-zero, okay, left hand side is tx, which is this. Right side is lambda x, which is this. Okay, lambda x1, lambda x2, and so on. So again, we compare the left hand side and right hand side. So look at here, 0 must be equal to lambda x1. Okay, and from here, since lambda is not 0, look at here, so x1 must be 0. And then look at here, lambda x2 equals x1, okay, one by one. Look at here, 0 equals this, and then x1 must be equal to lambda x2, which means this. Or equivalently, lambda x2 equals lambda x1. And x1 is 0, right? So again, we get lambda x2 equals 0. Again, lambda is not 0, so x2 must be 0. So if we continue this process, you will see x1, x2, x3, all are 0. Again, this is a contradiction. Again, this is a contradiction because here we said non-zero. Okay, so you can see no scalar lambda can be an eigenvalue of T. So what does it mean? It means T has no eigenvalue. So it means the spectrum of T, whatever it is, does not contain any eigenvalue. So do you remember when we said that when lambda belongs to a spectrum, so this lambda it is either an eigenvalue or another case was T minus lambda is not on 2, right? Okay. Now let's describe, okay, so far we know that the spectrum of T does not have any eigenvalue. Okay, now the question is, what is the spectrum? Okay, we want to identify or compute the spectrum. First of all, look at here, if lambda belongs to the spectrum, then the absolute value of lambda less than equals the norm of t. Do you remember that theorem? We said that the spectrum is contained in the complex plane, is contained in a circle centered at origin of norm of the radius of the norm of t. If I remind you, do you remember that theorem? We talk about this. The spectrum is contained in complex plane. It's contained in a circle, in the circle centered at origin of radius norm of t. Okay. So, okay, here. So, if lambda is in a spectrum, the absolute value of lambda is less than the norm of t, and the norm of t here is 1. So we get this. So from here we get the spectrum must be subset of these complex numbers. Okay, for simplicity, let's call this one gamma. Okay, so from here we know that if we have any element of a spectrum, then the absolute value of lambda is less than equals 1. So it means a spectrum is a subset of gamma. Okay, gamma. But this gives us a conjecture, or more precisely, so far we know that the sigma t, the spectrum, is a subset of gamma. Okay, but we claim that the spectrum is precisely equal to gamma. Okay, so if you want to, it means we claim that the spectrum exactly equal to this set. Okay, to prove our claim, we have to show that sigma t is a subset of gamma, that we have seen this is true. So only left to show the other inclusion. It means we have to show that gamma is a subset of a spectrum. So if we show this, we already have this. So this equals that, this implies that the spectrum must be equal to gamma. So we only need to prove that gamma is a subset of a spectrum. So it means we have to prove that if lambda belongs to gamma, then lambda belongs to a spectrum. Okay, we have to prove it. But look at here, when you say lambda belongs to a spectrum does not have any eigenvalue. So this lambda cannot be eigenvalue. So what kind of lambda is this? Look at the next page. So it means when we say we have to prove that if lambda belongs to gamma, lambda belongs to a spectrum, is equivalent to saying that t minus lambda I is not onto, because lambda is not an eigenvalue, right? So the other case happens. It means t minus lambda I is not onto. So we have to prove this. So take lambda in gamma, we have to prove that t minus lambda I is not onto. And remember, just to recall, t minus lambda I is a bundle linear operator on L2. Okay, now we want to prove this. Okay, suppose the otherwise. It means we suppose that t minus lambda I is onto. When you say is onto, it means if you take any element here, there is at least one element here such that this map, like for example like this, if you take y here, there is x here which is mapped under this mapping to y. It means if I take y here, there is an x here. Okay, there is an x here such that t minus lambda I maps x to y. Surjectivity. So suppose the otherwise. So we suppose that t minus lambda I is onto. Okay. Again, to get the contradiction, we consider two cases separately. Lambda 0, lambda non-zero. Okay. If lambda 0, look at here, if lambda 0, here t minus 0 I equals t. So it means we are claiming t is onto. Okay, if t is onto, you take this element in L2. This is an element of L2. Since t is onto, it means there is an element like x here such that t maps x to this element. So it means there is an element like this in L2 which is mapped to this element. So left hand side is 0, x1, x2, and so on, and right hand side 1, 0, 0. So now you compare. If you want the left hand side and right hand side to be equal, we get 0 equals 1. This is a contradiction. CONT means contradiction. So there is a contradiction. So it means T cannot be on 2. Okay, T cannot be on 2. It means we took this in L2, but there is no element to cover this. Okay, under T. Now, look at the next page. Now, suppose that lambda is non-zero. Okay, again, we are claiming that T minus lambda is on 2, right? So, if I take this element in L2, there is this element in L2 which is mapped to this. Okay, again, see what happens. If we calculate the left hand side, is easy. You get 0 minus lambda x1, x1 minus lambda x2, x2 minus lambda x3, and so on. And right hand side is 1, 0, 0, 0, and so on. Okay, now let's compare left hand side and right hand side. So this must be equal to 1, right? So it means minus lambda x1 must be equal to 1. So from here we get x1 equals minus lambda divided by minus 1 divided by lambda. Okay, there is a typo. This lambda 1, please delete this. Please remove this. This is a typo. Look at here, we get minus x1 minus lambda x1 equals 1. So from here we get x1 equals minus 1 over lambda, not lambda 1. There is a typo. Please remove this. And here, x1 minus lambda x2 must be equal to 0, right? So here you can see. From this equation you get x2 equals 1 over lambda times x1. And you get, and x1 is minus 1 over lambda. So you get minus 1 over lambda squared. So if you continue this process, you get xn, each xn equals minus 1 divided by lambda to the power of n. Okay? Again, there is a contradiction. Why this is a contradiction? Why this is a contradiction? Look at this page. Okay, look at the, yes, next page here. This one. Okay, there is a contradiction. Why? Okay, look at here. Do you remember we said that x1, x2, x3 belongs to L2, right? Okay, so look at this one. We said that this map to this, so this is an element of L2. So if this is an element of L2, so it means this series conversion. But by the calculation on the previous page, we get, look at here, x1 is minus 1 over lambda, x2 is minus 1 over lambda squared, and in general each xn is minus 1 over lambda to the power of n. But this, look at here, this sequence is not a square summable. This does not belong to L2. Why? Look at here, this series is divergent. Look at here, it means sigma minus the absolute value of minus 1 over lambda to the power of n squared is divergent. Why is it divergent? Look at here, do you agree with me? A simple calculation shows that this equals this, 1 over the absolute value of lambda to the power of 2 to the power of n. And do you remember this lambda is coming from the set gamma, so the absolute value of lambda is less than equals 1. So you take inverse, 1 over the absolute value of lambda is greater than equals 1, and this implies that 1 over the absolute value of lambda squared is greater than equals 1. So it means this is a geometric series. Look at here, this equals this. This is a geometric series, and the common ratio here is greater than 1. So if we have a geometric series such that the common ratio in this one is greater than 1, so that geometric series is divergent. Okay, so this is our contradiction. So this means, let me back here. Our claim is true. Okay, our claim is true. So the spectrum of this unilateral shift equals this set, all lambda such that the absolute value of lambda is less than 1, and the spectrum does not have any eigenvalue.